Hi, my name is Brian Q, and today I'd like to talk a little bit about my project at Oak Ridge National Laboratory, which is called Learning Continuous Scattering Length Density Profiles from Neutron Reflectivities using Convolutional Neural Networks. But first, I'd like to talk about how linear algebra has helped me understand the ins and outs of machine learning. On the left side, we can see the most basic type of neural network, the fully connected neural network. So basically, what it does is it takes in x1, x2, and x3, the input that you give the neural network, and then you multiply it by w1, w2, and w3, which are the weights of the neural network, and then you add a bias to it, which is b1, and you get y1, the output. W1, W2, and W3, as well as B1, are modified throughout the training process such that the model can keep on progressing and learning. On the right side, we can see the more specific neural network that I used, convolutional neural networks. The overall structure is that an input is given to the CNN, and then a submatrix of the input is convoluted to create feature maps, which are then pooled, which reduces the dimensionality, and then that is input into a fully connected neural network, which creates the output. But I think more importantly is how the convolution works. The convolution works with linear algebra, in fact. So in the bottom image, you can see that a submatrix is taken, it is multiplied by a kernel, and then that result is put into the feature map. And on the right side, you can see the more specific math, but basically what happens is it's 1 times 1 plus 0 times 0 plus 0 times 1, and so on. The kernel is changed throughout the learning process such that the model is continuously learning and being optimized. First, I'd like to give a little bit of a background on neutron reflectivity and scattering length density curves. So on the top left corner, we have a neutron reflectivity curve, or three neutron reflectivity curves, and our goal is to use that information to get the top right picture, which contains three scattering length density curves. So this generally takes a very long time just because we have to modify the roughness, thickness, and scattering length density of the two copolymer layers and the silicon oxide layer, as well as the roughness of the substrate. So even for just a two-layer system, we have to modify 10 different parameters just to fit one curve, which takes a very long time. So now I'd like to talk about how I use machine learning to mitigate these problems. So on the right side, you can see how I generated my training data sets. Basically, I gave the program that generates the simulation data sets, I would give it ranges for each parameter that you saw on the previous slide. So I would give it ranges for those parameters, and then within those ranges, it would choose a single number within that range, and then basically that would give you a set of parameters. And from there, it would be able to generate the correct neutron reflectivity and the truth corresponding scattering length density curve. And so at first, we tried to use one big training data set and use one convolutional neural network to try and predict all of the experimental data sets. However, this was very difficult and didn't produce very good results just because using one training data set to cover such a vast amount of data was too difficult, and the convolutional neural network was not able to learn very well. So we split this into 25 smaller data sets and trained one convolutional neural network on each data set. This is a method called ensemble learning, and basically it just decreases the richness of information in each data set and helps the convolutional neural networks learn. So these data sets differed in that for data set 1, for example, the roughness was from 0 to 10 and thickness was from 10 to 300 for the first layer of the copolymer. But for the second data set, the roughness was from 10 to 20 and the thickness was from 20 to 300 for the first layer of the copolymer. And so basically, these changes would be made throughout generating the 25 data sets, and then basically we would train one convolutional neural network on each one, and yeah, so Now let's talk about optimization that I used. Optimization was a big part of our project. So the first thing that we did was we had to choose our hyperparameters using Raytune. So in the end, it figured out that, it told us that the optimized set of hyperparameters would be 12 layers, and then the following other values for learning rate, weight decay, and batch size. So the structure of our convolutional neural network was it would optimize neutron reflectivity curve input, and then this would be convoluted, batch normalized, and ReLU'd 12 times, hence the 12 layers. And then that would be input into a fully connected neural network and then a sigmoid activation function. The sigmoid activation function would output a normalized SOD curve, and then we would denormalize that to give it physical meaning. So but for experimental data sets, since we didn't have the truth SOD curve, we would convert these SOD curves back into neutron reflectivity curves and compare it with the original input. So on the right side, we can see the results from that. And more specifically, the left picture is showing the results of a convolutional neural network trained on 10,000 curves. And on the right side, we have the results from a convolutional neural network trained on 30,000 curves. And so basically, this is just using the method of converting the convolutional neural network's SOD curve back into neutron reflectivity and comparing it with the original neutron reflectivity curve. So here are the final results using convolutional neural networks. So the top three panels signify the neutron reflectivity curves being input into the convolutional neural networks. And within each picture, you can see the original experimental neutron reflectivity curve, the manual fit method, as well as the convolutional neural networks fit. So so for the bottom three panels, you can see the comparison of the manual and convolutional neural network SOD curves to see how well the convolutional neural network actually does. And as you can see, it does pretty well, and I would say these are pretty good results.